I want to give a couple more examples of induction proofs. First of all, to get a little more practice with the idea, but also to go in a couple of new directions and illustrate that it's kind of a versatile thing that you can apply in a lot of different contexts. Hopefully this is a nice refresher as well, if you're getting tired of doing number theory all the time. So here's another example. A convex n-gon is a polygon with n edges, n sides, all the sides, which is convex. But maybe if I want to be precise about what that means, I mean, it's hard to be super precise without getting into trouble, but let's say with interior angles less than 180 degrees. So, you know, it's something that looks like this. This is convex, whereas something like this is not convex, because this angle is greater than 180. So we are familiar with this fact that the angles of a triangle add up to 180 degrees. So let's prove a more general fact. Sum of the angles in a convex n-gon is 180 degrees times n minus 2. Let me actually rewrite this. Is 180 times n minus 2. So for a triangle, which has 3 sides, this is 180. And as you add sides, you add 180 each time. So let's prove this. We will induct on n the number of sides of our convex polygon. So the base case, again, shame on me, I have forgotten to say it in the claim. For n greater than or equal to 3, this is true. I mean, maybe you didn't need to say this because the smallest an n-gon can be is 3 sides. If you have 2 sides, you can't really make anything with that. So the base case is going to be n equals 3. So this is just the original statement, that the angles of a triangle add up to 180 degrees. But let's prove this real fast, just for fun. So I'll give a little bit of an informal proof, but if we draw a general triangle that looks something like this, and we label the vertices A, B, and C, we label the angles, rather, then let's take this line, this side of the triangle, and let's draw a parallel line up here. And then let's observe that if you remember some of your basic facts from planar geometry, if you have 2 parallel lines like these, and if you have a line going through them, then the opposite angles are equal. So these 2 angles are equal, which is to say that this angle is A. And for the same reason, this angle is C. And this shows that the 3 angles A and B and C put together add up to exactly 1/2 turn, which is 180 degrees. So that's the base case. Now let's take the induction step. So let's n at least 4, and suppose angles of a convex n-1 add to 180 times n-3. So we're taking this formula and plugging in n-1. So we get n-3 here instead of n-2. And we want the angles of a convex n-gon add to 180 n-2. So how are we going to do this? So similar to the last time, the idea is to take our case, in the case n, and somehow reduce it to a little bit extra from the case n-1. So the way we do this is, say that we have some convex polygon, which I'm drawing a little bit informally, but we're looking at some small region of it, around some particular vertex. So choose a vertex. I'm choosing this one and drawing this little area of the polygon around this vertex. And what we're going to do is we're going to draw this diagonal of our convex n-gon. And what we're left with is, if we include this line, this area is now a convex n-1 gon. And here, of course, is the triangle. And we can see that the sum, well, let me leave out the sum everywhere, but I'm going to write it. But the angles of our n-gon are, so all of the stuff we're leaving out here is part of our n-1 gon. And then we have these angles on the n-1 gon and these angles on the triangle. And together, these, of course, add up to this full angle of the n-gon. These add up to this full angle of the n-gon. And what we're left with is the total angles of the n-gon is equal to the angles of the n-1 gon plus the angles of the triangle. And now we can apply our induction hypothesis to say that this is 180 n-3. This, from our base case, is 180. So for our n-gon, we get 180 times n-2 now, just as we were looking for. So that completes the induction, and that completes the proof.